Hello everyone, this is Jeon Peoljung. Today I will explain introduction to data structures. Today's topic is time complexity analysis, growth of functions. The textbook is Introduction to Algorithms by the Corman, Lager, Liebest-Stein, MIT Press. You can refer to this textbook. So syntactic analysis, the definition of syntactic analysis, a method of describing limit behavior. For example, let a function fn is n squared plus 3n. Fn is syntactically equivalent to n squared because n squared, this is dominant factor component. So increase n, the behavior fn is determined by this term n squared rather than 3n. So as n goes to infinite, that is fn approximately close to n squared. A syntactic notation objective is describe the learning times of algorithms. Example, insert over insertion sort, the worst case learning time is the big zeta n squared. Tn is time complexity. Input size n, we have this kind of polynomial a n squared plus bn plus c. This the highest order is 2, right? So the highest order dominant term, that's why we have big the zeta n squared. The usage, we can consider time complexity. Also, we can consider space complexity for given data structure and algorithm. We have 3 kinds of syntactic notations. So such as zeta notation, big O notation, and big omega notation. So you can see the target function fn is given, and then this fn is between cn gn function. This is lower bound, and the c2 gn is upper bound. Usually gn cn, okay, gn gn, right? So c1 c2 is coefficient, right? So two function is gaps is close to each other, and then fn gn behavior are syntactically close to each other. Okay, so in that case, the gn is a tight form for fn. The big O notation is fn's upper bound. Okay, cgn is upper bound, and the big omega notation case, cgn is lower bound for fn. Let's take a look definition of zeta notation. For given function gn, we denote by zeta gn. Gn is the set of functions for time complexity as follows. Zeta gn is fn. There exist the positive constants c1, c2, and 0, such that this kind of inequality. Okay, so fn is between cn gn and c2 gn. So c1 gn, this one is a lower bound for fn, and c2 gn is upper bound for O n certain threshold value n0. So once n reaches this lower bound, fn is always close to this sandwiched bound, the lower bound, the upper bound. Okay, so in other words, a function fn belongs to the set zeta gn if there exists positive constants c1, c2 such that fn can be sandwiched between c1 gn and c2 gn for sufficiently large n. So fn is one of element the set zeta gn. Gn is called an syntactically tight bound for fn. Let's take a look example. So in the middle we have fn. Okay, this one is c1 n squared is Gn C2 n square. Okay, so Fn between C1 Gn C2 Gn. Okay, according to the previous definition of zeta. The question is find C1 C2 and n0, and then we can say in the middle the function Fn time complexity is zeta Gn. Here Gn is n square. So the answer is first of all we divide this inequality by n square, so n square gone, and this one is 3 over n, right? This is 3 C2. Okay, so for any n at least 1, okay, greater than or equal to 1 in this inequality, so we can see C2 exists greater than equal to at least 1 over 2. So we have C2, right? Also the n0 is here 1. For any n at least 7 case in inequality 2, C1 is less than or equal to 1 over 14 case, we satisfy. So we satisfy both of them. So greater than 1, greater 7 case, we can say threshold is 7, satisfy both condition. And we can pick C1 is just this range, right? 1 over 14. C2 is lower bound 1 over 2, right? 1 over 2. So according to definition of zeta, so certain threshold n0, also we have positive constant, this one, right? C1, C2. And then eventually we can say this is Gn, okay? So the middle function, this is Fn, time complexity is zeta Gn. So you can see we have a positive constant, right? C1, C2, and 0. So we satisfy sandwich bounds. This is zeta Gn, okay? Let's take a look big notation, big O notation. Big O Gn is a set, the functions, okay? There exists a positive constant C and n0 such that Fn is positive or equal to 0 and upper bound Cgn. For all n, threshold is n0, right? So Fn upper bound Cgn. And then we can say Fn upper bound is big O Gn. In other words, a function Fn belongs to the set big O Gn if there exists a positive constant C such that Fn is at most C Gn for sufficiently large n, because we have a certain threshold n, and then always satisfy Fn is below or equal to this Cgn. So Gn is upper bound. So Fn is element of the set big O Gn. Gn is an asymptotic upper bound, which means approximately Gn is upper bound for Fn. Let's take a look at big omega notation. Big omega is a set of functions Fn. There exists positive constant C and n0 such that Cgn is a lower bound for Fn, right? Because for n is equal to or greater than n0, n0 is threshold. And then Fn is, you can see, always, okay, greater than Cgn. So up and down, right? But certain this n0 and then always, okay, greater than or equal to n0 for n case. Fn is always up over the, the same. This is, Cgn is lower bound. So in summary, zeta is sandwiched, asymptotic tight bound. Big O is upper bound, big omega is lower bound, okay? So in other words, a function Fn belongs to the set big omega Gn if there exists a positive constant C such that Fn is at least Cgn for sufficiently large n. Fn element of a set of functions Gn, right? And then this one, the Gn is asymptotic lower bound for Gn, Fn, okay? So eventually Fn's lower bound is Gn for big omega case. We have theorem 3.1 for any two functions Fn and Gn. We have Fn is set the Gn case. Gn is a tight bound if and only if Fn's upper bound big O Gn, Fn lower bound big omega Gn. In other words, if Gn is both an asymptotic upper bound and asymptotic lower bound for Fn, asymptotic upper bound is big O, this one. Asymptotic lower bound is big omega. Both case, Gn is asymptotically tight bound for Fn. Okay, now we'll see liter O and liter omega. Liter O notation definition. Liter O Gn case, a set of functions Fn for any positive constant C. This one, any positive. This is important. Okay, there exists a positive constant threshold n0. Okay, n0 is a positive. Okay, number such that Fn, and this is a proper upper bound, not equal, right? So C Gn is upper bound, the proper, not the same overlap. Okay, for n greater than equal to n0, right? So this threshold case, any positive number case, this is okay upper bound. Okay, so in that case, the Fn's upper bound is Gn. In other words, a function Fn belongs to the set liter O Gn if for any positive constant C, Fn is less than Cgn for sufficiently large n, as long as the n is greater than or equal to threshold value n0. Fn is element of liter O Gn. In that case, Gn is an upper bound for Fn that is not asymptotically tight, always upper. Okay, and omega notation. So liter O, liter omega Gn, a set of functions Fn for any positive constant C greater than 0. This is any positive constant C. There exists a positive constant n0 threshold. Okay, positive number such that Cgn is always lower bound Fn, not asymptotically tight over lower bound. Always Gn is lower bound for n greater than or equal to n0. In other words, a function Fn belongs to the set liter omega Gn if for any positive constant C, Fn is greater than Cgn. Fn is always upper, above of Cgn is Gn is lower bound, just rather than asymptotically lower bound. Okay, for sufficient large n, Fn is a function Gn's. Okay, this the lower bound element. Okay, so Gn is a lower bound for Fn that is not asymptotically tight. So examples. Okay, liter notation case, Gn n square, right? So in that case, Fn is always, lower, right? So this is upper bound. This is, yes, but this is the same, the order in polynomial, right? In that case, not, no. And omega notation case, this is lower bound, right? So order is the same. In that case, no. But this is above n always, right? So lower bound n, right? Yes. So let's take a look another definition, limit-based definition of liter notation O notation and liter omega notation. Liter O notation case, F and Gn, right? So Gn is upper bound, right? In that case, order is Gn is higher. So in that case, n goes to infinite case, this is going to 0. The function Fn becomes insignificant relative to Gn, higher order, as n approaches infinity. On the other hand, omega notation case, Fn is the higher order because Gn is lower bound, right? So in that case, we cancel some polynomial terms, and this is a higher order, right? So n goes to infinite case, this going to infinite, okay? So the function Fn becomes arbitrarily large relative to Gn because Fn is okay higher order polynomial than Gn as n approaches infinite, okay? Thank you for your attention. If you have a question, please let me know. Thank you.